we started out with practicing a couple of these, and let's go over them. The integration of sine of x is, well, if I say cosine, the derivative of cosine is negative sine x. This is positive. So if I got to flip this sign, I got to flip that sign. Cosine? Yes. So I've got to flip that sign, okay? It's the negative cosine of x from 2 pi to pi. So now I just throw those in and subtract them. So negative cosine of 2 pi minus negative cosine of pi. What is the cosine of 2 pi? Forget the negation. What's cosine of 2 pi? 1. It's 1, but then I'm going to negate it, right? So it's negative 1. Minus. What's the cosine of pi? Negative 1. And then when I negate a negative 1, it's positive 1. And I got to subtract that. Negative 1 minus 1? Very, very good. Very, very good. Of course, if calculators, you can type them in, and you should, to check your work. Okay? But these are simple ones. If these were on the final, these would definitely be in the multiple choice without the calculator. Okay? Second one, Xavier. What is the derivative of e to the x? E to the x. So if I have e to the x, what's the integration of e to the x? It's e to the x. From 1 to 0. E to the 1 minus e to the 0. What is anything to the 0 power? So I can say e minus 1, and that's a perfect answer. Well, okay, it's 2.718. If you want to subtract it, it'd be 1.718. But if I want an exact answer, that's exact. If you try to give me a decimal as an exact answer, you'd be right for a long time. Because it goes on forever. Sorry, it does. That's why I love saying the number e, and all the kids look at me. It's crazy.
So you put the two numbers in for e?
Yeah, this goes in for the x. The e is like pi. It's a number in the calculator. So e to the first minus e to the 0. Anything to the 0 power, anything is always 1.
Anything?
Anything. 1 billion to the power of 0 is 1. All right. Last one. Mr. Alex. What's the integration of this?
That's the inverse 10. It's 10 negative 1.
10 negative 1 of x. Very good. That was one of the rare occurrences with trig, the inverses. Remember, if we did the cosine, and I asked you for, it was just a formula to know it's 1 over the square root of 1 minus x squared. If it was this one, it was 1 over the, and it's a plus x squared. And if it was tangent, there's no radical in the bottom. Is it this with a plus? You think it's a negative and a negative? You might be right. I'm just trying to recall. It is one of those. All the cosines are negative. That's why I thought it was a minus there. It is one of those. But I'm just saying, trying to bring back some memory. It's real rare to see one of these. I just want to throw it at you again.
I didn't know that that's 10.
It's one of the formulas you have to remember. It's one of the things. So, sine is cosine. Tan inverse. Now, take this from 1 to negative 1. What did you guys come up with?
1.57.
10 of negative 1 of negative 1. Okay? So, what do we come up with?
Negative 1.
No times anything. I just do the inverse of tan and put a 1 there. Okay? You got 0? That sounds about right. You put that in a calculator or no? You do it out. You put it in a calculator. All right. Let me explain. All right? If you put this in a calculator, you get 0. All right? Remember, whenever I see this, that's like whose angle, when I get the tangent of it, will give me a 1. Meaning, if I was trying to figure this out, I could say tangents, this is the angle. It will give me the angle. In this case, it would be radians, right? Radians. Or it could be degrees. That's fine. It doesn't matter. So I want to find out what degree would give me 1 if I take the tangent of 45. 45, 45. So this would be 45 degrees. Or if you want to do that in radians, it's pi over 4. Pi over 4. So you can also say it's pi over 4 minus, we'll give you a negative 1. We'll give you a negative 1. If I have, well, if this is positive 1, 45 degrees, right? Isn't tan negative in this quadrant? Well, if I subtract the negative 45, should I have gotten 0? So let's check it. Let's check it. Hold on. Let's check. Let me get rid of this. This is what we're doing. We're in radians. Okay? And I want to say seconds, kind of 1 of 1. Minus, yeah, I'm just doing it again. Where are we? 10 seconds. 10 negative 1 of negative 1. You don't get 0. How come you don't get 0? Yeah, you're right. It's 1.57. I heard you earlier. I just wanted to work it out. So what is 1? Look at it. 1.57. What is that? It's half of pi, which is pi over 2, which means we're right here. It's pi over 2. This is negative 45, which is like negative pi over 4, isn't it? So if I subtract a negative pi over 4, isn't it like adding? Subtracting a negative? So that would be pi over 4 plus pi over 4, which is 2 pi over 4, which is pi over 2, which is 1.57x. All right? That one was tough. That one wasn't easy. I didn't expect you guys to get that. That one was tough. Some of you could have gotten it, but now you've seen it, you'll get it. Integrals. Here we go. Properties and rules for definite integrals. Okay? Just like derivative, integrals also have properties and they're very similar. Okay? So, order of integration. If I have the integration with the bounds from b, the upper bound, to a, the lower bound of some function, I can flip those bounds and just negate what my answer is. And it'll do the same thing. If I flip my bounds and I negate my answer, it will give me the same thing if I use the bounds before I flip them. That's it. Go ahead, go on. Yeah, it's recorded.
Is this the same one that, because in the book I saw, it had the same symbol, but it had like a little dash. Like,
we'll get to that. Yes, we'll get to that. That's going to be, I'll explain when we get to number 3, that it can be the same principle we're applying. Now, 0. Guess what this means? Take a look at the integration of my bounds. It's the same. When the bounds are the same, it's only 0. Think about it this way. If I have a graph, all right, let's call it x squared, parabola. That's the right side, that's the left side, good. If I'm on the bounds from 0, the area under the curve, right, that's what this does, to 2, okay, that's this area here. What if I wanted the area from 0 to 0? There is no area. It's the same point, you're not moving. You're not moving left or right at all. So there's no area, so it's 0. Yeah. They're rules. And we're going to practice these rules in the home run. It's simple, okay? Just make sure you have the sheet in front of you when you do the work, because it helps. All right? The constant multiple rule. What happens if I took a derivative that had a constant in front of it? Couldn't I take the constant out, take a derivative, bring it back in? Same rule applies here. So, Irving, to answer your question, if I'm going to take the integration of something that's negative, this is technically a negative 1. I'm multiplying it by. I can take this negative 1 out and put it in front here. I wouldn't switch the bounds, and it would be the same thing. I don't switch the bounds. If I take that out and switch the bounds, it would negate the negation and make it top. You see what I'm saying? All right. Sum and difference. Same exact rules apply. If I'm adding and adding, I'm not subtracting. But if I'm adding and subtracting different terms with only plus and minuses between them, I can take the integration of those terms individually and keep a plus and minus between them. Same thing with derivatives. Okay? And I like the word for number 5, additivity. Okay? I love that word. Now, what this is saying is if I take the integration of the same function, notice I both f of x here, from b to a, and then from c to b, okay? That's the same thing as taking the function from c all the way to a. If the upper and lower bounds match, then I can just forego it. You see how this is a b, it's an upper bound, that's a b, it's a lower bound, then I can just go directly from c to a. It's hard. I mean, when you're looking at that, you're like, wait, should it be A, B, then B, C? Let me show you on a graph. Everything's always easier with a picture. It's just two numbers. Like, let's say this is from 5 to, that's the upper bound, 4 here. Okay, 5 to 4. Then C has to be bigger than B, right? Let's call it 7 to 5. Well, if I'm going to take the area of the curve from 5 to 4, and from 7 to 5, I can take the area directly from 7 to 4, because they're right butt up against each other. Meaning, and that's the one I'll draw right here. If I have a graph, 4, 5, 6, 7, and I have this thing, I don't care, blah, 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 blah. And this first, right here, 5 to 4, says I want the area from here to here. And then I take this one, from 7 to 5, would be from here to here. Can't I just go right from here to here? That's all I'm saying. And just, I mean, why do 2 when you just do 1? Now, if they wanted it from 3 to 4, and then 5 to 7, I can't do that because they're not touching, they're not connected. Okay? But as long as they want this and this, well, then I can just go to the extreme bounds. That's all I'm saying. Okay? Suppose that f and g are continuous functions, and that the integration of f of x from 2 to 1 is -4. The integration of f of x from 5 to 1 is 6. And the integration of g of x from 5 to 1 is 8. Let's solve all these using that information. Look at a. Can anybody tell me what a is? Why is it 0? Yeah, that's the 0 rule. If the bounds are the same, it ain't going nowhere. What about b? Why is it -8? That's insane. Yes. G of x, the integration of g of x is 8. But when I flip my upper and lower bounds, I have to negate it. That's equal to the negation from 5 to 1 of g of x, which is basically taking g of x and negating it, which is 8 and negating it. Okay? So you see how these are? Not too bad. What about c? It's negative. You would have both been right. It is -12. Because this is a constant, I can put that up front. 3 times the integration from 2 to 1 of f of x dx. And this right here, if you look up front, is -4. 3 times -4 is -12. Good. You guys do D, E, and F. You can probably do it in a minute. And this is where we'll stop. We'll pick it up tomorrow. Okay?